So we're back to the 2024 Caltech Math Meet finals. And today we're focusing on problem number 32, which was the definite integral from x equals to 0 to x equals to 1 of e to the power arctangent of x over x squared plus 1 to the power 3 over 2. So let's see how we maybe would solve this problem. So with a problem of this nature, where you have x squared in the denominator, the usual tactic strategy here is substitute 4x with the tangent of theta. So we say let x be equal to tangent of theta such that dx d theta is secant squared theta, and that means that you can substitute for this dx with sec squared theta d theta. Now looking at the limit, when x is 0, the arctangent of 0 from this is going to be equal to 0. When x equals to 1, the arctangent of 1 is going to be pi over 4. Therefore, transforming this integration from the x domain to the theta domain would involve substituting for the limits with theta from 0 to pi over 4 over arctangent of x is theta, so we have e to the power theta, and then x squared is tangent squared theta plus 1 to the power 3 over 2. In place of dx, we have sec squared theta d theta. Now, tan squared theta plus 1 is the same as sec squared theta. So we are going to replace the tan squared theta with sec squared theta, right? Now, 3 over 2 is the same as square root to the power 3. So we're going to have to get the square root of sec squared theta and power it by 3, right? So here we have the integral of e to the power theta over sec cube theta times sec squared theta. So now sec squared theta and sec cube theta would interact, and now we have e to the power theta over sec theta as the integrand. Sec theta is the same as 1 over cosine theta, so the sec theta now becomes 1 over cosine theta, and that means that the problem now devolves to e to the power theta times cosine theta. Here the problem has become more tractable. There are two ways you can go about solving this. You could use integration by parts, or you could say cosine theta is the real part of e to the power I theta, in other words, the Euler relation. Or you could go the long way where you say cosine theta is the same as e to the power I theta plus e to the power negative I theta over 2. Whatever works for you, that is fine. So let's begin with integration by part, and I'd like to express e to the power theta as the derivative of e to the theta. And so integration by part states that if you have a product of function v and the derivative of function u, and you try to integrate that product, you get the product of u and v minus the product of u, function u, and derivative of v. In that instance, our u is going to be the theta, our v is cosine theta, so uv is e to the theta cosine theta with the limits applied appropriately minus the integral of u, which is the theta, times the derivative of the v, which is the derivative of cosine theta. Now, let's keep this as it is for now, and then we go ahead and say, okay, the derivative of cosine theta is negative sine theta, so we'll pull the negative out, so this sign becomes positive, and now we have the integral in this second item of e to the theta times sine theta. We do the same process, repeat it, and re-express e theta as the derivative of e to the theta, and then you continue by saying, okay, the product of uv is e theta sine theta minus the integral of e to the theta times the derivative of cosine theta, sine theta, which is cosine theta. And we realize that this is the same integral we started with, so we could call this I, and on the left hand side would have an I, obviously. So you can now take the I that is on the right hand side to the left hand side and make it 2I. So we have 2I is equals to first limit as theta tends to pi over 4 minus of this expression minus limit as theta tends to 0 of this expression, and the same is applied to this. And so in this instant, cosine 0 here is going to be 1, and this e to the 0 is 1, and so we're going to get 1 here. Sine 0 is 0, so this part goes to 0. Then here cosine pi over 4 is the same as sine pi over 4, which is 1 over root 2. And so 2I is equals e to the pi over 4 over root 2 minus 1 plus e to the pi over 4 over root 2 minus 0. Add this together, we get 2 of them. And so we have 2 times e to the pi over 4 over root 2 minus 1. Divide both sides by 2. That means that now we have I being equal to e to the pi over 4 over root 2 minus a half. And that means that our integral now from x equals to 0 to x equals to 1 of the arctangent of x over x squared plus 1 to the power 3 over 2 is the same as e to the pi over 4 over root 2 minus a half. And that's the answer that was expected. So another method that I could use to solve, and that hinted on it, e to the theta cosine theta integrated from theta equals to 0 to pi over 4, is saying that cosine theta is the real part of e to the I theta. And with this you could either use cosine theta being equal to e to the I theta plus e to the power negative I theta over 2 and still come to the same answer. But here we choose just extracting the real part. So this integral is the same as getting the real part of the integral of e to the theta times e to the power I theta. And that means that we have integral of e to the power 1 plus I theta, and that is the same as e plus e to the 1 plus I theta over 1 plus I, with the limits applied appropriately, and that substituted, you get what we have here. And so we can decide to rationalize the denominator, and that we multiply by 1 minus I theta, both the numerator and denominator, as we have shown here. Then what happens is that since we have a difference of 2 squares here, that becomes 1 minus I squared theta. I squared, sorry, on both the denominators here. And I squared is the same as negative 1, so this becomes 2 to both of those. And then we have separated this here, so e to the I the power 4 is the same as cosine pi over 4 plus I sine pi over 4. And we can multiply that out, and here we get cosine pi over 4 plus sine pi over 4 plus I sine pi over 4 minus cosine pi over 4. Sine pi over 4 is the same as cosine pi over 4, so this part just becomes 0. And so we have the real part of e to the power 4 cosine pi over 4 plus sine pi over 4 over 2 minus 1 minus I over 2. From here it's very quick to see that the only imaginary component here is this negative times negative. This is positive pi over 2. In other words, 1 over 2 is the imaginary part. So we're not interested in the imaginary part, we just want the real part. And that means that the real part is just since cosine pi over 4 is the same as sine pi over 4, which is 1 over root 2. So we have twice 1 over root 2 over 2 here times e to the power of pi over 4. And when we divide that by 2, we just get e to the power over 4 over root 2 minus 1 over I over 2 here, and we want to extract just the real part. So the answer here is that the integral here is I e to the pi over 4 over root 2 minus a half. And that's the same answer that we had found in the previous method. So either of the two ways of approaching it is fine. If you're very comfortable with dealing with complex numbers, that's also fine. Whatever you choose to use, that's okay. But it's been an absolute pleasure hanging out with you today. If you haven't subscribed to our channel, we do really encourage your support on this. Please subscribe to our channel. If you like what you see, please just press on the like button. If you know somebody who might benefit from these videos, please share with them. We would really appreciate your support on this. Until next time, have a blessed day ahead. Thank you.